will try to get the try to find another analysis of with some different materials and devices, and try to make a device with which device we can like uh, some two probe devices are also we make in this session, and try to find the transport calculations and thermoelectric properties of that device or material, and many more things we'll simulate and make in this session. So we'll start it soon. Before the let it be, I think it should be we should be started the session. So before the starting, I wanted to explain some application about the NanoDcal software. Since in NanoDcal software, you can work with the spin devices. If you're working with devices, so you can work with spin devices application, semiconductor devices application, molecular electronic devices, or the researchers who are working in the field of material science and chemistry also. He can also be have the they get the good information and platform for this application, and they can also work with the battery and energy storage type application, phonon and heat transport type application. This all type of application can be able with our software. They can software can be calculate all the things like analysis part, in which band structure, thermoelectric properties, and many more properties will show in this seminar. So let it get the started. Let started with the our software. So first we have to go on our device studio. So let it be. First I'll. So shall we start now? So I'll have to cut this device. Yes. So let it be started our session. So first we have to go on our user interface, that is device studio. So we'll go here and see again our pop-up window will show here, in which you create your new project. And if you have an already existing project, you can directly locate that location and you can browse it. So first we create the new project, or we can also go in the existing project where we yesterday's do. So in I'll save here. My location was here. So whenever you locate your project, like when you create a new project in using the device, there will always a HPF file are generated with that name you are saved, and another file are also generated, in which your all the calculations or parameters of structure coordinates, everything is there in this file. And their main file, which exactly take the device studio, is this HPF file. You can always, if you wanted to locate your project, you have to always know about the HPF file, and simply click on the HPF file and click OK. See, we are here, our the existing project where we are yesterday calculated. So now I will try to simulate and build some structure, material structure, and find some thermoelectric properties like Hessian phonon band structure, density, phonon density of state. This type of property we try to calculate. So first we have to import the. I will do this calculation with silicon atom. So I have to go on this file option, and I wanted to import the silicon from our local file directly. So simply go to the file and import and import local. So here, there is a number of materials are there with different dimension. We have to only use for 3D materials. In 3D materials, there is some semiconductor directory in which there is a silicon you get. So simply search it, silicon one. So this is your silicon. Now, so okay, this is your silicon device, silicon molecule. Now we first try to simulate this material with material properties with our NanoDcal software. So first, we have to create the SCF input to calculate the NanoDcal software. If you wanted to calculate their properties of the silicon molecule, where we try to do go with the NanoDcal software. So simply go to the NanoDcal and click on SCF calculation. You can all see this is the SCF file, SCF calculation for crystal. If you are if your this material will be device in form of device, here it will return in SCF calculation for device. So this is a crystal. So here written in crystal. So in which this is the SCF file for our crystal. So first we have to choose some parameters. So you can see here, if you wanted to change the electron temperature, energy cutoff, exchange correlation with different uh, uh, space type, and you can also get the K point sampling values. If you want to change the extraction control for better simulation, in which you can change their mix rate, and if you wanted to steps in maximum step, you want to 200 steps, you can also change this accordingly. If you wanted to give some energy uh, to this crystal, so you can give the energy from here. And if you see the basic set, here you can change, here you can choose the Hubbard terms. And in Hubbard terms, there is specific atom and their sub cells are shown in which you can define the values. And if you wanted to change the spin type, like collinear or general spin, you can select it. And after give the all parameters value. So simply click on generate file. When you click generate file, see this CF input for this crystal is generated. So simply you have to click on right click and click the run option. You can see here the pop-up window for the calculation run is shown here. If you have a better license, commercial or academic license, proper academic license, so you can choose the core number of core. It is core goes depends upon your desktop or PC or a server. It goes up to 32 cores. So if you choose this course, you can your calculation will be more easier and more faster. So click on run. So when we click on run, so here our calculation is in job status. You can see here the calculation is running. Now, if you are cut it cut it. If you wanted to see the status of your calculation, so simply you can see here silicon, and in it is in running condition. And if you see the what is the status, you can simply click on I button, and you can see that our calculation is started. And since in meantime we can try to find another parameter. So we'll click on NanoDcal and go to the analysis part. And now we have to find some values. So I will check some we think like we have to find like Hessian and phonon band structure, electron density. These things we have to calculate it. We calculate it here. So in Hessian, it will be completed. If you wanted to do with hands-on, so you can also do with your do this calculation with us. Uh, so now first we calculate Hessian and phonon band structure. After we calculate some thermoelectric property, that is ZT. So before the calculation of ZT, you must have the output of Hessian. So you can choose Hessian here, and you can see the in phonon right side. You can see here phonon band structure and symmetric K points. In symmetric K point, you can choose your Brilliant zone path according to your convenience. So here you can choose here, like I will choose, and if you have some your standard parameter, you can also convert it in your according, and simply click on apply. Then we go on to, if you wanted to change the number of key points, you can also change here and click on phonon, and you can see the phonon band structure. You can change their Brillouin zone path, and also you can change number of key points. So simply click generate files. So see our SCF calculation for silicon crystal is completed. And in log file, if you wanted to see the status of your calculation, see the all calculation for SCF calculation is SCF for crystal is done. And now we'll calculate the Hessian. So simply go to the Hessian.input file and click right button and run. And run. Same for phonon band structure. Go to the right and click run. So if you wanted to see the status of your calculation, you can see from the log file. See the calculation is started for the Hessian. Here, all the parameters inputs are mentioned here. What the things we have to calculate it. So Now, see the calculation is still running. In the meantime, when while the calculation is running, we can perform with some another material. So we will try to make the another material with graphene. So uh, we have to also find some thermoelectric properties of another material. That is, I will take the graphene nanoribbon. So see the how I make the graphene nanoribbon structure and make it into the uh, a structure and material, and I will then after I will find another parameters like thermoelectric property. So I will go on file and click see in build option. There will be another things is given, that is a graphene nanoribbon. In graphene nanoribbon, you can simply click if you wanted to see. If you see here, this is the graphene nanoribbon tool that you use for the make the nanoribbons. So I will take the an atom which is you can where you can put their crawl vectors. If you wanted to choose their if you wanted to change the atom, if you wanted to make the atoms like I here I will be make the carbon nanoribbon. So I'll change the here default click the carbon, and if you want I will take some values of n and m. So I will take the value of n will be 0, and for m I will take 4. Simply click on preview option. You can see here your uh, graphene nanoribbon, which is a carbon based, which is it is a carbon material, is created. If you wanted to add some hydrogen passivation, if so, your bond will be correctly uh, not vacant. So you can click here, like I will click passivate diagonal bond with hydrogen. So you can see here hydrogen bond all, is connected. So here we don't need to the hydrogen passivation. So I will uncheck and I will take this nano ribbon and build. You can see here your hydrogen nano ribbon, carbon nano ribbon, carbon graphene nano ribbon is created since the graphene make via carbon. So I'll make this nano ribbon into the crystal form. So I'll make the some vacuum into this material. So I'll go to the this tool. This is the convert to crystal option. Here I will choose some values. So I'll take the values of before the make this vacuum, I'll have to expand some values in this graphene nano ribbon. So simply go on build option and take the redefined crystal and type some values. Like I will take the in the direction of Z, I will take some values 5 that is and click preview option. So your this is the graphene nano ribbon which is we need. Simply click on build and you can if you wanted to see the see the this device into different view, you can click x view axis, xz axis, and yz axis. Also you can see we have y-x axis and z axis. So we'll take this. If you wanted to change the coordinates axis, So you can do with here, like if you here from this alternate axis. So see here the coordinate points are changing. So these things all are dependent your project. So next we try to find another calculation for this nano ribbon, and we'll try to find the transport calculation and thermoelectric properties of this nano ribbon. So we'll go to the first. We have to make the SCF input for this nano ribbon. So I'll go to the simulator option and see the your calculation is calculated for the silicon one. So for ASEAN calculation is completed, and now phonon boundary structure is the running condition. So in meantime, we will try to find another parameter for this graphene nano ribbon structure. So simply go on simulator options and then NanoDcal and make the SCF calculation. See, you can see here again your pop-up window for SCF calculation for question. It is all automatic detect this software, and we will choose some values like for case sampling. We'll choose this value will be default like 113. If you have another key point sampling, you can change according to your convenience. We'll take the exchange correlation same, and now we'll click on generate file. So uh, this is, you can see here the SCF input for this graphene nano ribbon is ready. Now we have to run this calculation. So simply click on run and click run. And you can see the your job status, your graphene nano ribbon calculation is started. If you wanted to see the status of your calculation, so you can see here from I button, and you can see the calculation is started. So you can see the here your main we can see here the silicon crystal, our phonon band structure and ASEAN dot input file is completed, calculation is completed. So simply click on right one and click on show view. When you click on show view, you can see the phonon band structure. This is the phonon band structure of silicon crystal. So you can see the things like this is the graph is phonon energy versus Brillouin zone path. And if you want this parameter, this value comes into the milli electron volt. And this is the graph in which you wanted to get the data into some specific range. You can change your values according to your calculation. If you do the calculation via theoretically, and if you wanted to change the name of your structure, you can change from here. And also if you get the some value, if you wanted to see this value into the MATLAB, so I will suggested you earlier previously. So here all automatic calculation dot phonon band structure dot plot equal to true file is automatic generated via this software. When you uncheck this and click save, when you run it, and when the running is calculated, the another graph will be shown in the form of MATLAB figure. So no problem. You can do it yourself. So now we have to calculate the ZT, that thermoelectric properties of this crystal structure. So so you can go here, analysis, and click ZT. When you go to the ZT, see this is a primitive cell system.object file is here. Here you have to browse that file where the silicon file is saved. So you go to the browse and locate the file where this file is saved. So we'll go here webinar and gallium arsenide, and we'll do with silicon. So go to the silicon one and go to the nanodecal. See the nanodecal object.mat file. This file we take for the Jetly. So click on this and click open. When you click open, this file will be come to the this file location come to this primitive cell. And if you wanted to change the K point sampling, you can change here. If you wanted to change the Q point sampling, if you have, you can change here. If you wanted to get data in between some energy ranges, you can get your data. You can put the values. If you wanted to uh, data, if you wanted to see your data in the specific temperature range, you can also set that data, and we'll click on see this value will be currently this value will be default, and we will also find phonon density of state. So we'll click on simply phonon density of state and go to the phonon density of state and save. You can see here another parameters you can save according to your convenience. So we'll click on if you wanted to projected density of state, you can click the projected, and if you wanted to project it on atom or coordinate, you can choose here. And if you wanted to index project, you can simply search from your directly file directory. So simply click on generate file. When you click generate file, there is the jetty.input file, and phonon density of state file is uh, so in your project directory. So simply click on jetty and click on run and click run. Now your since our already a graphene nanodibbon calculation is running, and if you want to, after this calculation is completed, then this calculation will be ready to the next calculation. And we have to also calculate the phonon density of state. So click on right and click run. See, the calculation is running. And if you wanted to see the status, so simply go to the log file and click right and open with. When you click open with, you can see the actual status of your calculation. So you can see here your it's still this one is calculating. So you can see here the graphene nano ribbon SCF file is running condition. So we'll have to wait some time. This calculation is take time according to your system and what type of your processor use and what type of your server use. The better server, better PC desktop will help you to the better calculations and take the less time according to another desktop or PC. So, so you can see here if you want it, this is we'll go for it and see our calculation is running for this graphene nano ribbon. In meantime, we can calculate. We have to also calculate the thermoelectric properties for this graphene nano ribbon. So we will go to the simply simulator option, and first we try to find the band structure of this this nano ribbon. So go to the simulator option and click NanoDcal and click analysis part and click band structure. If you can see here for materials, this all properties you can calculate like density of state, effective potential, total energy, band structure, charge, Hessian, phonon band structure, electron density, potential, trans channel, eigenvalues, eigenstates, full band structure, effective mass, complex band structure, Getty, phonon full band structure, phonon density of state, phonon trans channel modular. And in our in our updates, there are another parameters are also is developed conditions. So we here calculate the band structure. So simply click on band structure, and we also have to calculate the Hessian calculation. And we have to also calculate the phonon density of state. So simply click on the phonon density of state. So you can see here we find these three calculation. You can see here, as you can all know, if you wanted to choose your Brilliant zone path, you can choose from here, and their key point also. This value will be default for all of them. And if you want, if your energy range in the some specific region, you can choose from here, and we'll now in HCM, we have to go some. If you wanted to change values for this delta, and if you wanted to change the order of the value, you can write the values. And in phonon band structure, you simply go on, and we'll choose this value with. I will take this value with range between 0 to 0.5. So you can see here and click generate. So, maybe this value will be same here. Let's be taken. So you can see here your inputs files are there in project file directory. You can see the band structure. If you wanted to see the data of your band structure, you can see here. All the things that is your need for this calculation are shown here. And if you wanted to see this data into the MATLAB one, you can simply off this comment. When you uncheck this, this will be, you can also see the data in MATLAB figure. Will not use for here. So you can see this is a NanoDcal mat file is generated for this calculation. And this is the band structure calculation name and calculation dot band structure dot symmetric key points. That is the Brilliant zone path, and calculation band structure dot coordinate of the symmetric key point. The key points we'll choose here, and this is your key point sampling. And calculation dot control dot XML file. This is your script for your get the visual graph on the device studio. So no worry. So we have to simply, we want to see the output of this calculation. So simply go to the band structure dot input file and right click run, and click run. See, do again, go to the HCM, click run and run. And phonon density of state, click run and click run. Since all the calculation you choose it is running in running condition, after the calculation, their data will be shown here. So in the meantime, you can see this way you can find some properties of these properties of any material or a crystal. You can simulate. You can also calculate the values via your project, and here you can also, if you wanted to find the modulus of this structure, phonon trans channel, full band structure we calculated. If you wanted to calculate the complex band structure, effective mass, eigenstate. In previous, yesterday we are calculated the eigenstate, and if you wanted to calculate potential, so these all properties you can calculate easily. So click. We also try to calculate them. So click on generate file. When you click generate file, you can see here all properties. Their input files are shown here. You can simply go to the right, go them, and click right and click run option and run it. And same here, click run, run. For complex band structure, click run and run. for effective math dot input, click run, and run. And for here, you can see you can see most of the all properties of material using NanoDcal software you can solve. And basically, our NanoDcal software can calculate the material properties and device property as well. So we also perform the some device structure. We will create some 2 probe, 4 probe devices, and different type how to make these devices. With we will work with nanotube, and also we will create the defect of nanotube, how to create the defect into the nanotube, how to create the interface like structure. This all type of calculation we will calculate in the coming session. So here we can see here, if see we can see where we are calculated is running. So you can see here our calculation is in running session. So this will be maybe this will take the 5 to 10 minutes. So no worry until the calculation is running. I'm going to make the device using this device user interface. So we'll try to make the device of, I'll show you. So I try to make the build a aluminum and carbon chain device. So now we are next part will be the work on device with the NanoDcal software. So we'll go to the build a device. So see the one calculation is completed here. After the calculation is completed, your uh, in the job status, there will be shown, and your JACT for silicon is in starting to running, and you can see the status of your calculation. So now, in the remaining time until the still until the calculation is running, so we'll try to make the structure of device. So we'll go to the import option. So try to import some material from the local directory. So simply go to the file and click import and click import local. So when you open it, I need to this aluminum. So I'll go on see the one calculation of auto done. So you can go import option and click on 3D local and click on 3D, and we'll take from the material from the conductor, that is pure metal, and we need to aluminum. So we can see here this is the aluminum, and try to make this aluminum into the crystal, and using this we'll try to create some structure of devices. So we'll go to the build and click redefine crystal, and we put the some values. I will put the value. I have some standard value for this device. So here we put the -2 and it will be also 2 and 2. This will be 4 -4 and 4 also, and this will be 2, 2 and -2. This you can see here. This is if you wanted to see the structure, you can simply click preview and see. This is your aluminum crystal is ready. Now we'll click on build option, and you can see this is your molecule structure is ready. Now we'll do with some. We have to delete some redundant atom from here. So since you know, if you wanted to delete some atom, simply you have to go on this and select this. We double click on and slide and click. See here, this is the delete tool. You can simply click delete. When you click delete, your atom will be deleted. Now we have to delete this also. So go to the right and slide them and click delete. So we also have to change the orientation. So I will be take. I will go in. So I'll do it again. So delete it and delete it also. So now we have to make this structure into the crystal form. This is currently this is now this after the removing the redundant atom. Now it will make the molecule. Now we have to make this molecule into the crystal form. So we'll go to the convert to crystal tool. So here is convert to crystal tool, and now we'll put some values according to our convenience. So we'll click on this value will be in x direction 30, and this will be I'll choose 14, and this value will be 30 also. So you can simply click on build and click build and click center. Well, you can see here your this is ready. Now next go to the another part. So this is our one atom, one crystal is ready. Now we must have to take the another that device, another material. This will be a carbon. So go to the file and click a new crystal. See, this is also a type of tool where you can click your where you can make the device and crystal if you have your particular parameters. So click on new and click crystal. So when you click a crystal, you have to put some values. Like I will put some values for A. This will be a 30. So not one. This value will be 30, and this value will be, I'll put this value with 1.2 angstrom, 3 angstrom, and this will be also 30 angstrom. And now this is an orthorhombic structure. So alpha, beta, gamma value will be same as you all know. This will be a 19. So now here you have to define what type of crystal you chosen. So simply click on plus. When you click on plus, there is a default carbon atom is shown. If you wanted to change the, if you wanted to take the another molecule or atoms, so simply click on them and you, according to your convenience, you can change from here. So I will take the carbon and take their P1, their fraction coordinate I will be choose 0.5 and 0.5 also. Now this is ready. All the parameters are saved. Now click on preview. This is your carbon molecule with vacuum is generated. Now click on build option. Now we must have to make this structure. So I have to go on build and redefine and click on. I'll take some values. I have to expand this value into the B y direction via B, which is B, and click preview. Now, see, this is another material is ready. Now, using this aluminum and this carbon crystal, we make a device. So now, using this build option, build. Now we have to make the device. So simply click on build device. And if you wanted to see, if you can see here, this is a uh, 6 types of device you can make. This is a LR, that is stand for left and right structure. This is left, center, right structure. This is bottom, top structure. This is bottom, center, top structure. Forward, backward structure, forward, center, and backward structure. We will choose here bottom, center, and top structure. So simply click on this and click OK. When you click OK, see here is a bottom, center, top structure files in which you have to specify their values. So simply you can see here, this is the bottom electrode, this is center, this is top electrode. Okay, so I will, whatever you materials are make, you can directly import from here. And if you wanted to, like I will be take some value, I have to make this structure. So I will go to this and click on arrow, and I'll have to take the aluminum redefined crystal. So click, I wanted to at the bottom and the top will be aluminum. So click on this will be same. So click and in the center, I have to choose carbon atom. So I'll take the carbon atom, which is a crystal. So when you click, when you paste all values, simply click on match. Oh, let it be. Cannot be 500. Maybe some mistake. I'll do it again. Let's do it again. So click on this and aluminum, and send in center. I have to take this one, and in top this will be also aluminum crystal. So after this, I'll click on match. Okay. You can also browse from here if you have already a data in your particular directory. So no problem. You must have to so we will do it again. So before making this device, so let the check the material which is we are calculating. So how many calculations are done. So you can see here where nano ribbon band structure. Our calculation for band structure is ready. Now simply if you want to see this structure, so go into the band structure and click show view. And when you click show view, this is your band structure of your graphene nano ribbon is ready. If you wanted to see this values into some specific range, you can put the values. And if you wanted to see the Fermi energy level, middle of the band gap, or top of the valence band, or bottom of the valence band, it will be shift. So you can see here now when you click bottom of the, it shift also. So you can see here now another calculation. This calculation is, I think, calculated for this one. Okay. Yeah, man. This input density. Ma'am, your after the session, I will be uh, try to solve all the your problems. So no worry. Uh, since since the calculation are running, if you wanted to see this calculation, I already doing previously. So if your calculation will not calculate, I will be shown in my directory. So let's try the make this structure and what uh, see the what problem is facing we here. Uh, now we have to make the structure. So build option, device, bottom center, and our crystal is this is the bottom one, and this is the ammonium predefined. 10 fine. Maybe in this device too, there's something will be error. So no find to get this structure take the some problem faced. So no problem. I will be make this structure with another calculation. So I have 23 version. Let me check here. Maybe here this calculation will be possible. I have to make this structure so maybe something is find error in this structure. So no problem. I will make the another type of structure with the same thing. So let it be completed. This calculation. After the completed the calculation, I'll be do with the another. I will try to the make another structure of device. So you can see the Hessian calculation is calculated here, and I have another device. So I'll try to make this. So so nobody. I'll try to make a graphene nanotube, and so I'm going to make the nanotube structure with a graph of with this device studio. So simply we'll go to the build option. Here you can see the nanotube option and click nanotube, and you can choose your values, like what type of values you need. So first you need to what type of by using which molecule you wanted to create a structure. So we first choose the atom from our local directory. So click import local, and now go to the 3D materials and go to the semiconductor, find carbon. So you can see here, this is a carbon atom, carbon molecule. So we have to make this make a nanotube using this carbon atom. So simply go to the simulate build option and click nanotube. Then you click nanotube, you can simply choose some parameters, like I'll choose some parameters like if I choose 9, you can see the things. You can see this is the nanotube is ready. Now so this is the nanotube is ready. Now click preview option and click build. You can see this is the nanotube. Now we have to expand this tube into the with some certain parameter. So go to the build option and click redefine. I'll be expanding the direction of Z. So simply click on 3 and 60. Now this is the graphene nanotube and click build. Now I will be do it again. So no problem. And I have to expand it. So expand it more. So simply go on to the build option and click redefine crystal and click 3 also. So now you can see our nanotube is ready. Now, if you wanted to uh, add some, if you wanted to do some doping into this nanotube, you can do it from here. See, if you wanted to choose some doping, you can select that atom, and here the replace atom window, sorry, toolbar, click on replace. You can choose some, like I will choose gallium. So if you choose gallium, this will be at this point. Now this is the gallium atom included in this nanotube. So I don't need it. So I'll be take it carbon also. So will carbon default. So now we have to make this nanotube into the device. So when you need to make this device, simply here a tool, build, and this is the convert to device tool. Simply click on it, and there a pop-up window will be generated. If you wanted to, if you here you can choose the where you wanted to give the electrodes, like left electrode, right electrode, bottom electrode, top electrode, front electrode, back electrode, you can simply click and click the left electrode and right electrode. Since I have to use some, if you wanted to, you can see here, you can click preview. Since your electrode is ready, now this nanotube is in the form of device. So if you wanted to increase the thickness of this electrode, you can change the values. Like I will change this value, uh, like 8.35 to like 52, and since one is positive and another is negative, so click preview. So you can see the thickness will be increased. Now click on build. Uh, Now this is your device texture is ready. Now, the next part is we have to calculate this device. So go to the simulator option, NanoDcal, and we must have to, before the any calculation, we must have to the SCF calculation. So go to the SCF calculation, and you can see here, you when you since the device, uh, our another thing is device. So already it is default seen here SCF calculation for device, and one another parameter is included, which electrode, in which you can define the electrode parameters like left electrode, right electrode, and what type parameters, what type of values you need on, you have to put on electrodes, like what will be the electron temperature and what will be the voltage you have given. And there is a K points, and this is a basic setting, you all know. And contour integral, in which you can change the values like integral lower bound, circle points, real axis point density, real axis infinite mil. And in iteration control, you can, if you wanted to give some energy to this structure, you can simply check it and give the energy. Like I will be give some energy, the energy will be same with this. So this is in micron form, about to micro energy. So mixing variable is you can change from here like Hamiltonian matrix, density matrix, real space density, and in basis set you can choose your arrangement like atoms, element. If you want to see the Hubbard terms, you can check it. And in spin type, you can choose your spin type like collinear and general spin, and simply click on generate file. When you click on generate file, there are three types of SCF files ready. Since you can see here, there is a left electrode SCF file, right electrode SCF file, on device for device SCF input file. See, before the running the calculation of device to device.s input file, you must have to calculate all values of electrode. So first, your first priority is you you must have to calculate the electrodes SCF input file. So you can see here. Now click on run. Before the run, we have to see the what the things are in our electrode. So simply click on scf.input file, click open with, and when you click open with, you can see here their basic setting values, and their iteration control values like this is the energy we are adding, and maximum steps, and what type of mixing rate you choose, and these all things are given here. And in the electrodes are same, since left and right electrode are same, the value will be also same. So you can see here. Now this is the K point sampling, this is the Hubbard terms, and many more things are there. And you have to click on right and click run option. Now first we calculate the right electrode, then we must calculate the left electrode. Now, after the calculating the electrode, then go to the device output, device input. So in scf.input for device, we see open with, and you can see here in this in this SCF input file is generated for this device, and you can see here, this is the system.object of lead one, that is the electrode file. This syntax is generated for electrode here. From here, this the value you are calculated with for the electrode, it's automatically import this there or mat file, and you can see here all data are shown which is you selected in SCF input file, and after this you can change from according to your convenience and click on run option. Now this also running is in two condition. After the running will be done, all the values you calculated will be shown in your user interface. You can see here still the value which values is calculated. So SN is calculated. So it must be take the time. So no problem. I had already calculated this value. If you wanted to see, I'll show you. So uh, first you have to, I done this project in, so I'll show you the another uh, tab. So let me show you. Not this. Uh, See, I'll show you the parameters in another thing. So you can see here, I calculated this all the calculation previously. So I'll show the things. This is the band structure. I'll calculate it, and this is the phonon band structure. You can see this is the phonon band structure we are calculating still. And after the calculation, you can also get your information, your visual information from here. You can see if you wanted to see the data between the some specific range, you can check the you can choose the parameters, and if you wanted to see the phonon density of state, you can see here show view, and you can see this is the density of state, and phonon density of state, which is the number of state versus energy. And if you wanted to zoom it, you can simply click on this zoom in option. You can zoom it, or you can also see the values like this. And I will choose some values at some reason. So you can see here all calculation are shown here. So this is the phonon band density of state, and after this, I calculated the JEFT. So for JEFT, you can see here, if you wanted to see this data into the MATLAB, you have to go simply on MATLAB, and look at this file. And if you wanted to raw output of the data, you can simply nanodecal.mat file will be generated for the specific calculations. So you can simply go here. still it is still opening. So let me. So you have to simply locate your directory file where this calculation are happening. So locate this file and so you have to simply locate your file location, and I will select the folder. So it again. Things are not getting current. So see, you can see here. Now locate this file. You can see all the mat files are generated. If you wanted to see the data of band structure, and simply locate like you wanted to see the total energy, so simply click on and load this total energy dot mat file and simply write the data. When you click the data, their parameter will be so let it be uploaded. See, your data of your total energy is shown here. This is data, this minus 453.2314 millivolt energy is there. And if you as well as if you wanted to see the Hessian data, you can simply click load the Hessian.mat file and type data. You can see all the data, all the values of Hessian matrix is shown here. If you wanted to see the description, so you can write data dot description. So that manner you can find every data and every type of raw data in your mat file. So our session for NanoDcal software is still now today for completed today. Now another part of devices where I made it some WSET device, and if you wanted to see the another type of calculation like conductance and IV curve and photo current, this all the calculation I will be shown in the another session. Now in another another part of the webinar will take the my senior. So thank you very much, and I will be handle them. So thank you.
So dear participants, thank you very much once again to all of you for joining the session and so I would like to continue the session. Okay. So I hope till now you have maybe become some overview about the software, what the software can do. Okay. Maybe some of the people some facing some problem. Still, we will be helping you. So not to be worried, we will keep in touch with you one by one. We will call you and we will provide you all technical supports related to your problems. Okay. So I would like to continue one more session on the more insightful softwares. So one of the participants have sent one query to me that how someone want to import this font car file. One minute. So one of the professors sent me this contcar.cif file and want to see how to import it. Okay, so I would like to show you here how you can import the contcar CIF file. I click on import local and I would like to show you just a minute, 1 minute. Continuing the session. Okay. Sorry for the disturbance. So I want to open this CIF file. Now someone asking about how to import these structures. So the file is imported here. Now, if the bonding is not there, like you can see, there is some disbalance of atoms are there. The atoms are disbalanced. So why? Because the distance between the layers are huge. So that could be the reason. So you have to move the structures. You have to move this structure by selecting it, and then you will be able to make the proper like structures. If you want to see how this structure can be prepared, then you have to press it and you have to move it. So this is called move button. You can move according to your need. So we have given the license. If still the problem is there, then we can also take your system and we can help you. Regarding the Linux, maybe Linux, the GUI interface is there. User interface is there, which you can model the structures. For the simulation purpose, if there is some file missing in the Linux version, then we can look into your system separately and will resolve the issues. So till now, you have got the overview about NanoDcal software. Many of the things are still remaining for the device calculations, transistors calculations. So tomorrow session will be there on the user interface device studio with device calculation. And next session will be on MATLAB, this device studio, NanoDcal software in MATLAB. How we can run the calculation of material and devices inside the MATLAB. So that two session will be covered on tomorrow and day after tomorrow on the device applications. Okay. So before that, I would like to introduce about the new one another software. So that I want to introduce about the company that is called the Fluxim. Those who want to work at solar cell application, we have since multiple softwares. Okay, I believe people have installed it and they can also use the NanoDcal and Rescue in their computers. We can also have one-to-one discussion on your particular problems. Okay, and one of the queries were asked by Dr. Swanti Sangi regarding the electronic structure predictions. So I have questions raised this query to my developer. Okay. Once I will got the answer from the developer, then I will reply to your queries.
Thank you, sir.
So now I would like to introduce about these softwares. Okay. Maybe some of the software from this company will also be very helpful, because this software SatFOS that works on thin film applications, thin film solar cells, perovskite solar cells, OLEDs applications, tandem solar cells, perovskite tandem, and organic hybrid solar cells applications. So in one-dimensional, two-dimensional, large area PV module simulation, electrical characterization equipment are there, electroluminance, photoluminance measurement platform that is called FLOS. This is called FLOS, where you can measure the angle dependent EL and PL. Electroluminance, photoluminance. This is for degradation and stability analysis. And this is for perovskite stability analysis of multiple channels. So we are also representing the software, different software and hardwares. We have not given the license trial version of these equipment and software. But if somebody interested on this solar cells at a micro level, till now, whatever the talk you have attended, that was basically delivered at atomistic level, nanoscale molecular levels. But to work on micro level, layered based structures, like other TCAD tool do. Similarly, we have this SatFOS software, and there are other applications, solar cell LEDs with their publication, user, and all those things. So that's why I want to introduce in next half an hour session about the SatFOS, that how different kind of solar cell you can model it. So I want to open one of the software that is called SatFOS. We have not given the trial version of this SatFOS to you, but if somebody interested want to explore more commercial softwares, then definitely this is one of the software which is best for your use, and it is very fast in running the calculations. So I want to give you the details insight about this electrical optical characterizations of solar cells and LED applications. So let me introduce about this software that is called SatFOS. SatFOS is the name of this software, 5.4 version. This software is from different company. Till now, me and my colleague Sumit has introduced you about Teno Academic company that develop the software for atomistics kind of applications, molecular application, and quantum transport, DFT, and EGF. But if you want to work on drift diffusion methods, then ray tracing transfer matrix, then this SatFOS is useful. We have a sophisticated manuals and tutorials. So we will also share you the complete manual and tutorials of NanoDcals also after this workshop, because we have simulated so many projects that you may have seen live. Okay, so that project which we already done in past, we can share with you by uploading the Google Drive. You can also run in your computer and just to evaluate it as much as, so that you will become more convenient and user friendly with the software applications. If we talk about this SatFOS, there is manual and tutorials are there. In the manual part, it is completely the background information of the softwares, the models, the equations, the parameters, and different analysis, theoretical input. So once you click on the manual page, you will get to know the back inside about the applications. So about the models, which models is there, which equations is there. So you can see here, this is different equations, different models. It is there. So for the background information about the SATFOS, the manual is there. Okay. If somebody want to get the trial version of this SATFOS, we can also offer you so that you can check how this software is also convenient for your micro levels, solar cell, LED, optoelectronic device application, along with microelectronic transistors. Even the tutorial is there. In the tutorial, step-by-step process with proper screenshot is there, and you can model different solar cell applications. So let me show you here. If somebody want to work on LED application, this is like my first electronic OLED structures, where you can work on different the process with proper screenshot is mentioned. People can follow this process and they can prepare the LED very quickly and easily. It is very fast in running the calculations because normal DFT calculation software, whatever you are using DFT application, that takes a lot of time in the simulations. But this SATFOS will work on drift diffusion methods. So it is very quick to run the job. It will get your simulation result within 5 minutes, 10 minutes, 2 minutes, or 20 minutes. It will not go beyond hours. So that's why for statistics calculation, drift diffusion calculations, solar cell, LED, this tool will be very helpful. I will try to show you live demo how it can be done. So you can see the next session, my first byte OLED modeling. So if you will follow this procedure, you could be able to model the structures. And if you want to make the solar cell, you can see my first solar cell simulation. So in this step-by-step example, we will present how to perform the optical solar cell calculations. So optical analysis of solar cell, then electrical calculations of the solar cells. So optoelectrical, both calculations can be performed simultaneously. This is like the process which you can follow and we can prepare it. Okay, now I would like to show you in software how we can create it, the different structures. So I would like to start from scratch. I click on this 1 minute. New option to create the new project. But before that, I would like to start from run as administrator so that I will get all the privileges. To get the full privileges for background calculation, I started as an administrator so that the background permission will not come during the calculations. Now, if you see here, I have the empty project. This is empty project where surrounding air layer is there. Then there is called layer substrate. Next layer we can define as a, let's suppose ITO. And we can add more layers. So I can click on add layer. And then I can define the full transport layer, active layer. Next layer, let's suppose you want to work on perovskite application or any element, any organic material, perovskite material, silicon material, you can take it. And then I can click on new, another element that is called electron transport layer. And again, I want to click the bottom contact, metallic contact, aluminum. And then I want to take air on the bottom side. Now this is one structure that I would like to simulate here. So whatever I have mentioned here, the layer structure, that will display in my right side layer structure tab. Now here you can see the default thickness is added. We can define different, we can manipulate this thickness value. So let's suppose you want to define 1 micrometer. Instead of nanometer, there is unit nanometer, micrometer, millimeter. So I can select on micrometer and accordingly it is selected here, micrometer. And if I want to select this ITO as a 2 nanometer, then whole transport layer as a 30 nanometer. Example, perovskite layer as a 10 nanometer. This is, let's suppose, 40 nanometer. This is 10 nanometer. And this is whatever air. There is no significance, but we can define. And this software is basically having a module, optical module, electrical module, emission module, optical plus electrical, advanced optics modules. So I want to enable the module. Top toolbar, you can see these are some different modules. So if you want to perform the optical calculation, you can see this is an absorption module. Absorption module is basically required for optical analysis, where you can calculate the photocurrent, ISC, or absorption in the specific materials. Now, these are different material name only. This is material name and this is the thickness. Right side, you can visualize the structures. Now, to calculate the optical property, each material is having some refractive index. So this air layer is also having some refractive index. So I will go to this refractive index tab where I can define the constant refractive index that is called real and imaginary part. H in this rescue and nanodecal, we were calculating the refractive index of the material. But here we are defining as an input of the refractive index. So material calculation can be performed in the rescue or even rescue to calculate the refractive index. And this set force can also use at micro level at device simulations. So that integration between two software could be the possible. So whatever the material property you calculate by using rescue or nanodecal software, that material property you can put it here. Let's suppose you want to calculate homolumo from the nanodecal software. You can calculate the homolumo. You can calculate the concentration. You can calculate the dielectric constant. That you can put it here. You can calculate the refractive index. So that you can put it here. So this is like material plus device. Both can be aligned to each other. So that's why I wanted to show you this software where material application at atomistics level, device simulation at micro level can also be performed. So this is different material, air, and then you can find this substrate. Then this is called ITO. And ITO layer, each material, we have to assign the refractive index. So the refractive index of the material sometimes dependent on the wavelength. Okay, wavelength of the material is changing and refractive index, real and imaginary part is changing. As you have seen, the rescue has calculated the refractive index with respect to frequency or energy something. So that the frequency is changing and real and imaginary part were changing. So that's why each material refractive index we can calculate from there, and then we can define as an input here. So initially I have some already loaded material property. So I want to click on this file, and there is an option called new option, import option. If you want to create your own material, then you can create your new optical material by defining NK data, real and imaginary part. You can click here and put the value, whatever you have calculated from rescue, you can put it here. I can click on this add button, define the wavelength value in first row. Second row, you can mention the real part. Third row, you can mention the imaginary part. Then again, click on add button. Sorry. This is like 390 nanometer as an example. In second row, you want to define the new wavelength value, real part, imaginary parts. And then again, It is like I'm defining the value which I have calculated from rescue. So that type of research you can also perform. I click to define the wavelength value, then real part and imaginary parts. So let's suppose I have calculated the refractive index from rescue, and that value you can also put it here. This is a graphical script, and this is a graphical form and a script form. Both are possible. So if you are expert in writing the code, you can copy paste the code, and accordingly the script will be generated in the graphical forms. So both are integrated to each other. It is bidirectional. Either you can write the script or you can put it in the graphical user interface, and that materials will be used in the device calculations. So I want to say that the rescue and nanodecal works at DFT calculation at molecular levels. Rescue can calculate the material property, and then you can perform the device simulation using nanodecal. You will also learn a lot of things in device in tomorrow and day after tomorrow session in the nanodecal session. Okay, but here this session, why I want to include it in that, because we are also going to perform the device calculation here and importing the material, new property which is not available. We can calculate from material simulation and import here. We also have our own database of the material. If you click here in the import section, you can see the material refractive index database. It is basically a competitor of Escapes Bundy. Escapes Bundy is very small tool, very little tool, where basic functions are there. But if you want to work on broader level applications, then this another commercial tool where a lot of advantages will be there. I will show you how. This is one of the database of refractive index, real and imaginary part, which has been calculated, or taken from some reference papers. So if you see here, there are so many refractive index database is taken here. You can find there are so many refractive index file is there. .nk is the extension. You can see .nk. .nk real and imaginary part. .pl extension that stands for photoluminance. And .em extension represent the electrical material, semiconducting material. So NK is the optical material, EM is the semiconducting material, and PL is the photoluminance data. So you can see here there are a lot of materials are given in our library. So if you want to perform some device calculation at micro level structure, you can find this software, could be very useful for your research as well. Now, since I have selected ITU, so I will go to the itu.nk file, because it is the wavelength dependent refractive index which is given in our library. So I choose the material from my database and click on open button. Now the database has been loaded in my dashboard from my library. It is imported from the library. Similarly for HTL layer, if let's suppose HTL layer, I want to use some material, I click on file option, click on import section. As an example, I want to take Spiro omitted .nk file refractive index. Then click on perovskite, click on file option, click on import option, and go to the import. These are perovskite material. These materials contain the refractive index and semiconducting, homolumo, dielectric, mobility, and other recombination and excitomes. I want to enable the only optical methyl ammonium, this CH3 PBL3 perovskite layer, and click on open it. Then I can click on ETL layer, electron transport layer, and click on file options. And here, let's suppose I want to use P3HT PCBM. So I go there, P3HT PCBM. I have selected and click on load it. The next layer is called aluminum. So I want to import all material refractive index, real imaginary part. Click on import and select aluminum.nk file. And then click on open. Now each material I have assigned the refractive index. For optical calculation, so let's suppose I have given this name solar test optical property. This is name of project and let me run the calculations. So simulation, you can see it is very fast. You can see the optical key figures has generated incident power, normal incident power, ISC of HTL layer, optical efficiency of HTL layer, perovskite ISC value, perovskite optical efficiency. Each material it is calculating the short circuit current. So whatever if the some refractive that optical ISC value is there, it is calculated. If you would like to see the Cauchy-Shockley quotient limit, you can click on this photovoltaic and optical band gap and click on run button. The optical band gap is defined and then click on this one. You can find the Shockley quotient, fill factor, JSC, VOC, and Shockley quotient efficiency. You can multiply it by 100 with the direct incident power, not direct normal incident power. So this is all given here. Okay. If you would like to see the absorption profile, this is optical absorption profile. Which material will get absorbed more or right? So that's fine. This is optical calculation where the perovskite layer, how much light get absorbed, ETL layer, aluminum layer interface, HTL layer. So the optical absorption profile is displayed. If you want to perform the absorptance, this is for absorptance for total layer structures. For specific material layer absorptance, you can find this layer absorptance graph. So this advantage for unipolar layer structure. If you want to see this green one, violet, and this one and pink one. So each material, these are different materials which is displaying here. Blue region is called at bottom one with a 0 substrate. This is for green layer. HTL layer is called pink one, refractive index. And this one is called perovskite layer. This layer is for perovskite layers. So each material, which material will get absorb your light? So that absorptance, stack contribution, transmittance, layer specific absorptance, reflectance, at material level it can calculate. If you would like to make the device optical and electrical calculation simultaneously, then you have to enable this module. The battery sign module is there. That is called drift diffusion. So I have enabled the optical module as well as the drift diffusion module. These are two modules which is enabled. For perform the electrical calculation, I have to define the which layer is electrical layer, which layer is semiconducting layers. So I click on this ITO and I want to click on this general and set this layer as electrode type. Because ITO I want to use as electrode, aluminum which I want to use as electrode, and in between ITO and aluminum, all these layer HTL, perovskite, ETL, these layer I want to use as a semiconducting. That will make my device. So I click on this checkbox. It will enable the device. Now you can see in this right side, the layer structure, energy level. In the energy level, homolumo value is same because it is taken the default value. But the user can change according to their needs. So how you can change? You can go to the semiconducting tab, and in the semiconducting tab, you can find this homolumo value is there. You can find this homolumo. You can find this is called homolumo energy levels. And this energy level here, we are using as an input. In the set for software, we are using homolumo, dielectric constant, refractive index, electron mobility, hole mobility as an input. But by using rescue nanodecal, we were calculating the material property, where we were calculating as an output, but here we are using as an input. So that is for material specific, and this software is specifically designed for device calculations. That is a two difference in that. Now, if we see here, the charge transport calculation is possible in the set force, and ion transport calculations. So anions and cations and charge transport, both kind of transport calculation is possible. So you can see the default energy level, dielectric constants, electron mobility, acceptor doping, these are defined. But the value of HOMO-LUMO and dielectric constant will not be same for HTL, perovskite, and ETL. It will be different, right? So I will use here. 1 minute. So here you can see this is a HTL layer where we were using Spiro as a HTL layer. So I want to import the semiconducting material apart from optical material. Earlier I imported the NK file, optical material. Now I want to import the semiconducting material. So you can look into here. You can see these are all semiconducting database of semiconductor layers. So these are all .em extension, where .em represent for electrical material. So .em extension represent the electrical semiconducting materials. Now I want to import the material for my Spiro. And click OK. So from the material file, it will load the HOMO-LUMO value, density of states, dielectric constant value, and other electron mobility. If it is field dependent, it will load here. Now the next layer is called perovskite layer. So I want to import the semiconducting property of perovskite layer. So I click on this import button, perovskite button, and I want to import this perovskite ions and click on import. Now you can see this is second layer, energy level. The difference you can see, the LUMO value has been changed. Okay, LUMO value has been changed for this perovskite layer. Similarly, ETL layer, I can click on ETL layer and click on import layer. And I want to use P3HT PCBM as electrical material and click on load. So now the energy level for each material has been changed, and the dielectric value is also different, and electron and hole mobility is also different, because I have imported the material property from my database. So that are two type of device calculation you can perform. One is called at atomic scale device calculation using density functional theory. Another one is at micro level, TCAD kind of device simulation, which you are seeing, visualizing right now. And once you have done it, then you can go to the depth diffusion setting or absorption setting. This absorption module for optical calculation and depth diffusion module for electrical calculations. So I can go to the absorption module, and then you can find there is an option called single wavelength, or you can sweep the wavelength. Single wavelength, where you can define this wavelength range, and you can define some illumination spectrum. That is called sun spectrum. AM0, AM1.5, global spectrum, direct spectrum. That spectrum of the light you can fall on your device for solar cell application. So this is a different spectrum. AM 1.5. If you click on this browse button, you can find couple of spectrum file is already given in our library. So if you want to use any spectrum, you can see AM0, AM 1.5 or wavelength and intensity. One is column will be the wavelength and one column vertically will be the intensity. So wavelength horizontally and vertically intensity. If you have your own data of wavelength and intensity spectrum, that spectrum you can follow in this software. So that's why if you see here, the red graph, red lines that representing the total spectrum. But the blue area where we have defined in this particular wavelength from 380 to 780. If we want to change it from 390 to 795, the wavelength range, we want to follow the spectrum. So that's why this spectrum we can define by using this green layer, which will automatically show it to you. So this is for a spectrum input that we are putting on our device. And then drift diffusion is there, which will help you for steady states calculation, for transient simulation, for impedance correct calculation, AC impedance, for AC analysis, and IMPS, intensity modulated photospectroscopy, photocurrent spectroscopy, and voltage spectroscopy. For that purpose, you can use the steady states and transients. Now I can click on this run button to simulate this device structures. So I click on this run, you can see there is an arrow button that is called run calculation. We have not given the license trial version for this software, but if somebody interested, then we can offer it. This I have enabled the optical electrical. Now basically what you have done, we have defined the voltage. Let's suppose this is 0 voltage. Steady state solvers are there. I want to sweep the value. I want to optimize my structures. So what I will do, I will click on the sweep mode option. This sweep mode option will help you to define the minimum value of unknown parameter and maximum value of unknown parameters. So I can click on this 3 dot option, which is given here, 3 dot. And then either I can define wavelength, temperature, voltage, thickness, dielectric constant, mobility, HUMO-LUMO, any value. Let's suppose you have no idea how much will be the dielectric constant. You can set minimum, maximum, and software will perform the calculation on each steps. So that's why if you want to use voltage biasing, you can select this electrical and select the voltage. Let's suppose you want to perform from -1 volt to plus 1.5 volt with the increment of 0.2. So it will run the calculation at -1, -0.8, -0.6, -0.4, -0.0, 0.2, 0.4, 0.6, up to 1.6 volt, it will perform the calculation. So -1 to 1.6, I have mentioned it as an example. So let it run the calculation by variation of voltage, how the device characteristics will be changed. That study we can perform. I click on this run button. The calculation has been run and you can find the electrical key figures. This is calculated value. Simulation are done in few seconds because it is not DFT here. It is drift diffusion method and it is in one-dimensional calculations, which is very fast algorithm. It will take 2 minutes or 1 minute or 5 minutes or 10 minutes, dependent on type of structure. You do not require high-end cluster. Normal laptop, whatever you are using it, it can also be good enough for that kind of calculations. We can provide you the dongle-based license in future if you have any plan for purchase. So dongle-based license where you can put it into your dongle and you can also use on your personal laptop. So cluster will not be necessary for such type of softwares. It can calculate the, I have not defined the proper values, so that's why conversion efficiency is showing 0, but VOC, JSC, something is defined it. If you want to plot current voltage, this is device current. Device current from -1 to 1.5. Minus 1 to 1.5. Okay. And if you want to see the electrical field, this is for electrical band diagram. Electrical band diagram between the electrode. From minus 1 volt to plus 1 volt, how the band gap will change. So this is band gap. LUMO value is there in red color. This is called LUMO 1. And this bottom one layer, this one layer, blue one is layer, that is called the HUMO, highest occupied molecular orbital. And this is called energy reference Fermi levels. So this is like all curve HUMO-LUMO graph. You can see the band diagram for LUMO. You can see the HUMO band diagram. You can see the energy reference Fermi level for N type, for P type. So all graphical representation and curve graph, you can plot it easily. There are some other characteristics you can also plot. Charge density at minus 1 volt to plus 1.6 volt. So if the variation is there in your characteristics, then a study you can also perform the charge density, charge generation, electrical characteristics. This is for electrical characteristics. This is for recombinations. And this is for recombination parameters. You can see your recombination area. Potential, you can see the potential graph. And if variation of voltage is there, the voltage variation you can visualize. This is one parameter which I have sweep. If you want to sweep the multiple parameter, let's suppose you want to sweep the thickness also. So you can click on add button. And now next time what layer you want to sweep. Let's suppose you want to sweep the perovskite layer thickness. So I go to the layer option, perovskite layer option and thickness. So I have defined the perovskite 10, but I want to sweep from 5 nanometer to 150 nanometer and with the increment of 5 nanometers. So I want to sweep 2 parameters at a time. So I can click on this run button. So 2 parameter voltage and thickness are sweeping. That's why the little bit simulation time is increased, but still it is fast. If you have multiple more parameter, temperature also, HUMO-LUMO also, doping concentration also, mobility also, multiple parameter you can sweep and you can see the variation of different input. So unknown parameter, if you have not known, the software can do the calculation and find out the property. So that's why this sweeping function, which you have seen here, it basically give your minimum value, maximum value, and with number of steps for the iterations. Software will do the calculation on that particular number of points, and then it will run the job and calculates your value. So simulation is running, which you can see here. Now you can see this is called potential at minus 1 volt. And if the voltage variation potential is there, you can see it. Similarly, bottom side, you can see the thickness option is also there. This is for thickness from 5 nanometer to 150 nanometer. And for that, if the variation is there, you can study it. Similarly, the potential is there at 5 nanometer thickness, at 75, 80, 100, 10, 150. Potential variation, you can zoom particular region, you can visualize it. If you want to export your data, let's suppose this is one graph, okay. You want to export your results, you can right click and save in the form of image. Save image, PNG form, JPG form, PDF form, SVG form. These format you can also save your data. If you want to save in the form of text file or Excel file, the data file can be saved in the form of text or Excel. So that you can plot in Origin or other softwares. So data, whatever it is written, you can also export it. If you see here, this is called band diagram at 1 volt and thickness of 5 nanometer. Similarly, the thickness you can increase of the perovskite layer. Accordingly, the band diagram will plot. Okay. Recombination and other things. And even the optical analysis. Absorptance you can plot at -1 volt and 5 nanometer thickness. If variation will be there, that will be plotted. So this is a way where you can plot the all curve. You can see the current maximum power, fill factor, open circuit voltage, short circuit current, voltage, maximum power, conversion efficiency. As an example, it is showing you. I want to show you the list of example. So this is one of the example for solar energy yield calculation. Glass, ITU, P dot, P3HT, PCBM. So let me run the solar energy yield calculation for this particular example. This particular example is basically running the calculation with particular date and time, because the spectrum may not be a standard. Sometimes standard the spectrum is different on location wise. In Mumbai may be different spectrum, in Delhi may be different spectrum, light spectrum, intensity and wavelength. Kolkata may be different spectrum, Chennai may be different, Hyderabad may be different. So that's why these are different spectrum where we can define the specific location wise spectrum. Not only AM0, AM1.5 global or direct spectrum. This is the elimination spectrum with location and time. So if we want to define the location, we have to define the latitude, longitude, elevation, date, time. Default example is there, but with the change of the date and time, how the light absorbing by your device is varying. That study you can also perform it. That's why if you see here, you can see this calculated incident spectra, direct spectrum, and diffuse spectrum. The spectrum which diffuse on the device on particular date or particular time. Date and time is very important. This is energy yield calculation. So on which date you will have more energy yield or generated power, incident power, solar angle light, that study you can perform, or even the photocurrent, on which date you are getting, or you are getting the morning time, evening time, night time, at what time you will get the highest spectrum. So that's why this is for solar energy yield calculation, optical analysis. Some absorption you can calculate. This is for absorption. Multiple layers are there to calculate the absorptance, layer-wise absorptance. Each layer is absorptance, reflectance, transmittance. So the options are there, which you can plot multiple layer at a time, and you can export your data in the form of image or in the form of data. So image format data export is possible, and text format or Excel format data export is possible. If you want to see other analysis, you can see this is for solar EQE AC biasing voltage. In this particular IMPS, intensity modulated photovoltage, the frequency, amplitude and frequency are defined. So in this left side, you can find these are all examples. These all examples are specifically for perovskite, tandem, thin film, organic, hybrid, impedance, capacitance, conductance analysis. Now you can see the simulation has been done. You can plot the electrical AC impedance calculation. This is amplitude, wavelength, AC impedance. This is AC EQA, AC current with voltage. If there is variation with respect to negative biasing or positive biasing on the current, you can also plot it. You can see in the graphical form, in the imaginary part and the real part, including the responsibility for photodetectors applications, AC current power responsibility. And this is responsibility with current by power, with amplitude, phase, and wavelength respective, and voltage respective. This is with respect to voltage. And wavelength, if wavelength is varying, by which wavelength you will get that responsive graph of AC responsibility. Even this is graph called device current with the wavelength. If you want to see at voltage with variation of wavelength, by at what wavelength you will get the accurate IV curve. So you can plot like that. And this is graphical representation based on Langevin recombination, without recombination, even the power density, power conversion efficiency, with negative to positive biasing, wavelength and voltage, wavelength and voltage variations, power conversion efficiency there. It may be up to divided by 100, and then we will get to know the maximum power and power density with the graphical one. So even if you are talking about many more complex structures, you can see this is one more complex structure that given as example, SNO2, fullerene C60, perovskite, nickel oxide, interface hoping layer interface, middle ITO, two terminal junctions, amorphous silicon N-type intrinsic buffer layer, silicon N-type buffer layer to buffer layer, P-type HTL, bottom ITO. This is more complex structure. We can also get it simulated. So I want to take few other. This is one another example where ITO, old transport interface, perovskite interface, C60, fullerene, and AG as a back electrode. So top electrode is there, whole transport is there, interface between the perovskite and whole transport, interface between perovskite and electron transport and silver. Absorption module is enabled, depth diffusion and sweeping. 4 parameter at a time is sweeping. So voltage is sweeping, trap density for N-type and trap density for P-type. It is sweeping with recombination sweeping. I can run the calculation. So let it run the job. If you want to see the semiconducting property, you can see this is all semiconducting features. Different type of mobility, constant, field dependent, field temperature, extended Gaussian disordered. These are different mobility model. Excitons is also possible. Traps is possible, single energy, and other traps. Ion transport is possible in anion and cations. Recombination are there, Langevin, Auger, bimolecular, simplified. Recombination of semiconductor, impact ionization is possible. So these are some different models that will help you to improve your efficiency of your output. If you want to see this device current, you can see this is the device current value and voltage variation, IV current variation with respect to concentration. Concentration of interface traps. So you can vary the parameter, whatever you want to vary. Either you want to vary the wavelengths or you want to vary the bottom interface. This is like IV curve. So it is, these are 4 graphs: current density, recombination current, Langevin recombination, SRH recombination. That's why the blue, pink, red, and green. These 4 graphs are showing with recombination effect. Without any recombination, with recombination, Langevin recombination, SRH recombinations. So according to these 4 graphs, the IV curve is plotted. So that's why you can see this is a graphical output for the combination. Similarly, the other trap interface trap density output. This is for trap density variations. Even the power density variation, if it is there, power density variation and electrical key figures. If you want to see the fill factor, maximum power conversion efficiency, or Venn diagram, This is for Venn diagram, 0 volt, plus 0.5, 0.9, 1.1, and interface trapping. If any variation is there, that will also display. So this is basically one of the tool which I wanted to show you, that this software may also be, many people work on device applications. Okay. So some of the brief idea I have given about solar cell. Similarly, if you want to work on LED application, this is for LED, different emitting devices, PL measurements, electroluminance, radiance, CIE color diagram. For that purpose, multiple emitter layers you can set. Like this bulb fan is having multiple emitter layers. Even this full OLED is there, single emitter layer, multiple emitter layer, different material we have used, that it run the job. And you see here the simulation is done. IV curve is plotted at 160 Kelvin temperature. So temperature variation is performed in this particular structure. How do I know that? You can see sweep setting temperature from 160 to 340 with a 20 increment. So 160, 180, 200, 220, 240, like that. It will run the job. So you can see this is a device current with the temperature variations. If temperature at 175, 250, 325, and internal quantum efficiency, power density, Venn diagram, charge density plot. And if you talk about the MAC property, this is for CI color diagram. This is CI blue, green, red with wavelength respective. So if temperature is there, you can see the temperature variation on the color index. Luminous efficacy is there, and device efficiency, EQE. If you want to see the luminance, this is for luminance, and this is radiance characteristics, current efficiency, peak emission intensity, even other emission. If you want to check the emission, this is for emission graph, emission characteristics. So all curve and graph. With S-pole rise, without S-pole rise, normalized emission is there, white emission is there. So based on temperature variation, you can plot different curve. Okay. Similarly, so many other things are there. Software is very broad for different application. This is one of another structure: anode, HTL, EML, EML2, ETL, gold. I can click on run. Simulation is running here for this particular full doped LED structure. And you can see the reflected color, emitted color, intrinsic color. Reflected, emitted, intrinsic. Radiative dipole density, non-radiative recombinations. Absorptance, reflectance, transmittance, emissions, normalized emissions, like that. So you maybe got to know about the basic about this software as well in today's session, along with the NanoDcal, because I wanted to show you more innovative software to you. So I think today's session, 2.5 hours, is basically a long session, but we have tried to continue so that you will not become bored. If you have any questions, so you can ask your questions, and tomorrow we will again continue the session with the device simulation. My colleague Sumit will demonstrate you how you can make the device structure, different device simulation will be done. Even in MATLAB also, you will perform different device application. If any questions you have in your related to your software, or even in the using of the software trial version, you can unmute your mic and you can please ask to me. So there is one of the participant asked about, let me show you. Remember bilayer graphene, so cannot be perform simulation for that structure. Resemble bilayer graphene. You can perform the simulation of bilayer graphene, that is possible. We know there is a bond between layer in case of 2D material like bilayer graphene. Would be a bonding between the layers as the software is unable to simulate the structure. No, it is not compulsory that bonding would be there. Without bonding, it can also simulate the layer structures. We want to make bonding, that is possible. Without bonding, it can also simulate. Nanoparticle on iron sheet for anti-corrosion property in acidic environment. For deposition of nanoparticle, let's suppose silver nanoparticle that you were talking about. You can click on this plus sign and click on this silicon button. And then either single element you want to add or multiple element of carbon atom you want to add. This is the main thing. So for chain of the 20 nanometer thickness, you have to create the chain first. And then you can add, like here, I have added the silicon. Okay. Now, if I want to move the silicon, I can move the position. I can move wherever. So this is one silicon crystal. If I want to make chain, I can also make the chain. You can see here this one silicon nanoparticle I added in my device. So if you have a long chain of the material nanoparticle, you can add it in between the layers, and the software may be perform the internal calculations. So that's why the license is given. The research part need to be done by you because you may be better knowing about the better analysis. We can only guide you how the software can use the features available that will make your job easier. So participants have any questions? Just to explore the software which we have given to you, and for information like how you can take after the training also, you can visit the channel where we already posted many videos. As a reference, you can take it. Live session, if you are facing some problem, then we can help you. So you can visit the Simple Technology Innovative Research and go to the video section. And these are all videos are available. You watch it, perform it, implement it, and maybe you will find interesting this tool. So thank you fam to all the participants from my side. If any questions, you can also ask. Kindly continue tomorrow at the same time, 3 p.m. My colleague Sumit will demonstrate all the device features. You can use it for the device modeling, device simulation, even transistors. You can also try and start working on the software. That is important. Until unless you will not use the software, then you will not get to know the complete output. You start it, you may be facing some problem, we can help you after the training as well. Then you can provide your feedback, how the software is much useful, either it is useful or how much the feedback you have to provide us. I hope the participants are getting my answer. So now I want to quit the session. Thank you for attending and please be live 3 p.m. tomorrow.